All right, welcome all. As I said, this is fun with microcontrollers. The URL for the slides for this presentation are there on the title slide. I will also be showing this again at the end, so if you don't quite get it this time, you'll see it again soon. So, quick thing about me. As I said earlier, my name is Scott Irwin. I have been working at Bloomberg Engineering over 10 years now. I joined in 2014 as a senior engineer and as a team lead. I have also been a Python educator within the company and for other ventures. Within the Bloomberg engineering community, we have these things that we call guilds, and one of those guilds is about Python. I've been a leader in that guild since 2018, and I have been its co-chair since 2021. So the subtitle is about building a digital sundial, but what do I actually mean by that? So we're going to start our story by looking at the end. So this is where we're going. This is a photograph of the digital sundial, which I actually have here with me, that is running Python on a very small device. So what do we need to get to the end of this story? We need data, we need hardware, and we need, of course, Python. So the data is these sun event times. So things like sunrise, sunset, when the various types of twilight begin and end. We are using the data, or I am using the API provided by sunrisesunset.org. They have a simple, free REST API to where you can get this data. Usage is limited to reasonable volume. That's from their website. But for this device, we only need to get the data once a day, or when we first turn on the device. They do require, if you're going to use the data for your own projects, they do require that you show attribution to them with a link to their site. And there we go. Using the API is as simple as sending a GET request to the API endpoint. The data that you need to provide is the latitude and longitude of the location for which you want this sun data for, what date you want it for, the time zone identifier so that it can format the date and times in the time zone appropriate, and there are a couple of different formatting options on how it can be done. So this is just a sample of one of these data, and the details aren't particularly important to go through one by one, but what is in here is the date and time for astronomical twilight beginning and ending. This is when the sky first starts to lighten, well before sunlight or sunrise, as well as there are a couple of other definitions of twilight. And then it has down there on the bottom the sunrise and sunset times. What we then do is we take that data and we map it onto a circle. This circle represents the 24 hours of the day. And so those times that we're getting in the data represent the boundaries between the segments of the day. And so just as a reminder, this is what that graphic translates into when we actually put it on a computer display. All right, now that we have the data, what about the hardware? So to build this project, we needed a few things. We needed a microcontroller that supports Python. And just to give you a sense of how big or small these are, this is an example of one of these microcontroller boards. This is essentially a computer on a chip, but it doesn't run a full-blown operating system. It pretty much is a dedicated microcontroller, and if you can see, it's about the same size as my thumb. We needed a display because obviously we want to draw our sundial. And then we also wanted a real-time clock. This is so that when I turn off the device, we still retain the date and time, so when we turn it back on, we know what time it is. And then the last thing we needed is Wi-Fi so that we can connect and get the data from our API point from the vendor. The specific hardware that was chosen was the microcontroller went with the Adafruit ESP32S2 Featherboard, which is, Featherboard just happens to be this form factor. And I chose that one because it has a Wi-Fi module built into the board in addition to having the microcontroller. And just to give you a sense of what that looks like, that's the microcontroller. You'll notice that the pins are not soldered onto that. That's one of the things that you are expected to do as a hobbyist. So side effect of this is I also learned how to do a little bit of soldering. Similarly, we needed the real-time clock board so that would maintain our time even when the device was powered off. We went with the DS3231 Precision Real-Time Clock Featherwing. Featherwing is basically another board that's the same size and shape, and they're meant to be stacked up so that you can have a very small footprint for your device. And then the last thing that we needed was the display, and I went with the largest resolution display that I could get that would just conveniently work. This is a 3.5-inch display, and on the back of this board is the sockets to where I can just directly plug in the Featherboard. So this made integrating my components together very, very convenient. All right, so we have our data, we have our hardware, and now we're ready to use Python to put it all together. So Python on microcontrollers, the fun part of this is that we have direct access to the microcontroller board components, and we can also connect and have access to, from Python, low-level components such as sensors, displays, cameras, motors, accelerometers, and there's a long list of other items. So this is a chance to use Python at use a high-level language like Python to interact with very low-level devices. Of course, nothing comes for free. There are some limitations. Because it's running on a resource-constrained device, some of the Python standard library modules are not available. A couple that I bumped into that I would have liked to have used for this project were data classes and enum. They just weren't available. There are other modules that they are available, but they are available in a specialized form for these devices. So an example here are two that I used: the Adafruit datetime in order to get my datetime objects, and Adafruit requests in order to do my HTTP calls. Here we're using CircuitPython. CircuitPython is a fork of MicroPython, and they maintain parity with the upstream. The nice thing about CircuitPython is it's very beginner-friendly. If you have a board that supports MicroPython, you just plug it into your computer. It shows up as a USB drive on your computer, and you can just start dragging code onto that USB drive or editing the code directly on the drive itself. And so you get a very quick and easy feedback loop. You can also have the option of running the REPL there, so you can do easy experimentation. CircuitPython is integrated into the bootloader for the microcontroller board. This is what boots the board up. Since every board has different hardware, there's a different boot controller for each device. Just to give you a sense, this is where I got the bootloader for the particular microcontroller that we used, and this is off of the circuitpython.org website. The other nice thing about CircuitPython is that it has a very active open source community, a lot of contributors, so there is a large number of modules available. For the board itself, it included modules that were very handy in this project. It included things like collections, math, SSL, time, the OS module. In particular, I needed the os.getenv. The CircuitPython library specifically is the board module. That encapsulates the details of the microcontroller board itself. The Adafruit bus device, this allows us to talk to the attached Featherwing devices that we're using. Display I/O and 4-wire, these were modules I needed to talk to the display. RTC, which is the onboard real-time clock that's on the microcontroller itself, as well as socket pool and Wi-Fi. These were necessary for doing the Wi-Fi communications. Some additional modules that I ended up using was Adafruit itertools. Of course, we're dealing with date time, so I needed the time zone database, the Adafruit date time, the real-time clock, this Adafruit DS3231. This encapsulates the details of that particular hardware, as well as the Adafruit register was necessary. And then there are a couple of libraries here for talking to the display, including the display chip, this HX8357, and then a couple of libraries for working with the Wi-Fi. As I mentioned, the board module is built into CircuitPython. It provides access to board-specific objects. 4 of which that I used in this project were 2 of the individual pins that are on the board, as well as the 2 serial buses, the protocol buses that the board provides. So the serial communications, the first bus is the inter-integrated circuit, referred to as I2C. This is a 2-wire synchronous serial bus. It's used by the microcontroller to communicate with lower speed peripherals. And here on the slide, you can see the board.I2C call. That is getting the object for communicating with that bus and passing it to the initializer for the real-time clock. And this is basically connecting the off-board real-time clock to the local microcontroller board. Same thing for the serial peripheral interface, the SPI. This is a 4-wire synchronous serial bus, which then allows us to do full duplex. And this is the serial bus that we use to talk to the display. And this is also where we use the 2 pins, the D9 and the D10 pin, to handle flow control. All right, so now we're ready to talk about the core application. CircuitPython, to keep things beginner friendly, it just picks up and executes your code when you load it onto the device. It recognizes a couple of different Python files, one of which is code.py. And so all of the implementation is in code.py plus some loaded modules. And in that application, we define where we are in the world in terms of our latitude, longitude, and time zone. We then initialize the board's real-time clock from the external real-time clock. We get our current date. We initialize the display. We then create and show the initial graphical elements, those segments of the day, and as well as putting a time indicator. So we just have a single hand that shows roughly where we are in the solar day. And then we just loop forever. And we go to sleep for a little while, we wake up, we see, do we need to move the hand? If not, we go back to sleep, come back, and so on and so forth. And then when we cross from, say, the 27th to the 28th, we then fetch the new solar data from the API, and then we redraw the screen to update the segments that you see on the display. To initialize the onboard real-time clock, this is where we use the RTC module. We get the access to the real-time clock object itself, and we just force its date time to be the same as the external real-time clock that is attached to the device. And then to, just to keep the code a little cleaner, I wrapped the details of that into this function called current UTC time. For initializing the display is a similar sort of thing. Here we're passing the board object because we need several objects off of the board into this library that that sits off to the side. And basically it takes the board, pulls off the necessary pieces of information, including the SPI bus. It then creates this 4-wire object that allows us to connect to that display bus. We define our width and height, and then we initialize our display with that. The graphical elements, we're using a library called Display.io. The docs, which are available on the CircuitPython website, and this allows us to interact with the display in using high-level objects instead of having to address individual pixels. The element objects are created using Adafruit's display shapes module, which is also documented. In particular, we're using two objects. We're using the arc in order to draw the individual segments of the solar day. And then we're using the triangle shape to draw the indicator. Wrapping up, to summarize, Python provides an easy way for us to get started programming embedded systems. It allows us to do exploration of working with these very low-level devices. With some data, a small amount of microcontroller hardware, and a bit of Python, we were able to build a portable IoT device with a graphical display. Some possible enhancements that could be done in the future is it would be nice to have the date shown on the display. It would be nice to have small hash marks to indicate the rough hour of the day around the edge of the clock. And what would be really nice is to have a GPS to get the current location, because that is currently coded into the software itself. But that does require an external antenna that is not small, which is why I did not choose to do that initially. So these are the references. So the talk, that's the URL for this talk. It's hosted on GitHub. The project is also on GitHub. The code is in the main branch, and the code or the markdown for these slides and the CSS and that stuff is in the GitHub Pages branch of that repo. As a reminder, the solar day data is coming from sunset.org or sunrisesunset.org. CircuitPython.org is the place that you can go to learn all about CircuitPython. And Adafruit, I give them a little shout out just because they provided the hardware. They didn't provide, I bought the hardware from them. But it turned out to be a very convenient place to get all the bits and pieces that I needed. And with that, what I do want to show a little bit here is the code. So as I mentioned, everything is in this code.py. And so this is, if we scroll down to here, this is the main program, and this is basically what I outlined on the slide. This is where we're sort of setting up the system, getting the data that we need to do, setting up our display. Here we're setting our background color, creating the initial set of arcs, creating the initial time indicator, and then we move on to just looping forever and checking to see whether we've reached somewhere where we need to update one of the graphical elements. So with that, I think we're ready to take questions if there are any.
Thank you so much. Again, thank you so much for the nice presentation. The floor is open now for some questions, and I will start off my questions. How long did it take you to build this? And maybe everybody wants to know, how much did you pay in total?
Okay, so how long it took was, it took probably a month or two of a little bit of an evening, a little bit of a weekend, so it's hard to say what the total amount of time, and there was a lot of experimentation. So I tried a couple of different microcontroller boards and before I settled on the one that I did. In terms of cost, if we look at the components, we can see the microcontroller board itself was about $25 US. The real-time clock was another $14, and the display was about $40 US. So about less than $100 US to build the whole thing, plus the cost of my time.
Thank you. Now, if you have questions, please raise your hand. I will bring the microphone. I will give you some time to think, and while you think, I will ask a follow-up question. I never touched hardware. Is there anything that could go wrong or that you did wrong to break the hardware and you had to buy new stuff, or is that kind of friendly for beginners to touch?
So because of the hardware that I chose, because I chose this form factor of the feather wings, I really just had to solder on the pins. And so there was nothing, I did not break any of my hardware. I did buy some things that ultimately I didn't need, but I didn't know that till I got a little further into the project. I could have started out much more conservatively.
Okay, thank you. Any other questions for Scott? Please raise your hand. Oh, 2 questions. I will come to you with the microphone. There were 2 questions. Who wants to go first?
Where did you get your motivation from? Yes, but I'm not good at English, but I feel like I've been able to work on interesting ideas or project. Maybe because I've been too overwhelmed my daily tasks. So I'm interested in your fun project. So where did you get from motivation?
So part of the motivation came from just a long interest in working with hardware. Actually, when I went into university, I started out in a computer engineering degree, and then quickly realized that I enjoyed the fun part, but I didn't want to do that as a job, and I ended up doing something else instead. But I keep coming back and getting interested, and CircuitPython gave me a way of using my Python skills to interact with hardware in a way that I haven't been able to do in a while. Once I decided I wanted to do a hardware project, the inspiration for the actual device came from an app that somebody showed me that has this same idea, where the idea behind this app is that you shouldn't focus on exactly what time it is. It should be more like human-centered time. It's like, where am I in the day versus where am I in the microsecond? And so I thought I'd see if I could build my own version of that.
Okay, next question.
Classic question, I think, but I kind of want to hear, if you had one piece of advice you could give to yourself before you started the project, what would it be?
Keep your ambitions small. Because it's really way simpler than you think it is. I thought it was going to be much more complicated, and I did a bunch of things that ultimately, they weren't useless, they were helpful, but I didn't need them to do the project.
If I can have one more. What was the most expensive piece of hardware you bought that you ended up not needing?
Not needing, I ended up buying 2 displays. One that was smaller, and then once I realized how small that device was, I ended up buying the one that I ultimately used. So that was probably the most expensive piece.
Thank you.
Thank you very much. Oh, there is more questions. I see one more question. Just give me a second. Please.
Yeah, I'm really glad that someone asked the inspiration question. That was also something I was very curious about. And I'm wondering how often you get to do projects like this and what your next project might be.
I don't have a next project, so that's an easy answer to one. I have a very busy life, and so I have too many hobbies. And so this one kind of fits in between the other hobbies that I'm busy with. So it's hard to find the time for it sometimes.
Yeah, absolutely. I'm glad that you mentioned, though, that it's easy at least to do little by little, in the openings that you have through the day. Yeah. Thank you so much for your presentation.
Thank you. Any other questions? We have a little bit more time. If not, okay. 3, 2, 1. Okay, then one more round of applause for Scott.
Thank you.